So now we're going to talk about working weak acid-base equilibrium problems in specific, but we're also going to talk about working equilibrium problems with small values of K and the special situations that creates that in some ways makes our calculations much easier. Okay, let's consider a solution made 0.040 molar in some generic acid HA, right? And so if we consider the dissociation of HA, right, our HA in water will dissociate to form hydrogen ions in water and some, right, basic anion in water, right? And if we consider our ice table, right, initial change equilibrium, right? If we're at 0.040 of that, we haven't made any hydrogen ions, we haven't made any of the anion. If X dissociates, then we're going to get X of the hydrogen ions and X of the basic anion. 0.04 minus X, 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 right? And so we can set up that 1 times 10 to the minus 6 is equal to X times X times 0.040 minus X, right? And we can solve, right? We can solve that for X, right? If we expand that, we get X squared minus 1 times 10 to the minus 6x, plus 1 times 10 to the minus 6x minus 4 times 10 to the minus 8th equals 0. And if we solve that, right, we get that the most reasonable value of x is 1.995 times 10 to the minus 4, right? And that is equal to the equilibrium concentration of hydrogen ions, right? And so if we take the, if we find the pH is equal to the negative of the log of that 1.995 times 10 to the minus 4, right? We get a pH of 3.70, and I know this is invalid, 0.275, okay? Now, right, we said before that, right, since our problem is given in two significant figures, we're only multiplying and dividing here, so our answer would be in two significant figures, and the figures after the decimal point are significant in a log number. And so those two numbers would be the significant numbers. So our pH would be 3.70, right? After we did all of that work. Okay? Right? But one of the things that we notice here, right, if we put this back, right, is that our x was was this very small number, right? 1.9, that was a terrible 995 times 10 to the minus 4, right? So if we look, right, if we're finding our final concentrations and we look at this one, right, so our final concentration of our acid is going to be equal to our 0.04 minus the 1.995 times 10 to the minus 4. And if we do that subtraction, you end up with 3.9805 times 10 to the minus 2, right? Which is, gee, this number, right? This number is really close to this number, right? 4 times 10 to the minus 2. As a matter of fact, if we round it to our two significant figures, we get the same number. So in essence, subtracting this from this gives us an answer that doesn't matter, right? So could we have just not worried about, right? Could we have just not worried about subtracting that x there because it's so small, it doesn't really make a difference when we compare that to that, right? Those two numbers are so close to the same. Could we have ignored that x when we subtracted it? Okay? So let's look what happens, right? So let's consider that possibility. Let's just ignore that x and work our equilibrium problem that way, right? And so we said that our Ka is 1.0 times 10 to the minus 6, right? And that's going to be equal to x times x divided by 0.04 because we ignored the subtracting the x there, right? And so we get 4.0 times 10 to the minus 8th is equal to x squared, right? And then you get 2.0 times 10 to the minus 4th is x, which is equal to your concentration of hydrogen ions, right? So we've got 2.0 times 10 to the minus 4 versus what we got with the quadratic are 1.995 times 10 to the minus 4, right? That is a difference of about 0.25%, right? That's all the error. And if we use this number to calculate a pH, we get a pH of 2.69897. And again, considering we've only got two significant figures, if we round that, we're going to get that same number. So we get the same result whether we use this x here or not, right? If we leave it out, our calculation is much easier because we don't have to do the quadratic, and we get a number that is so close to the number that we get when we use the quadratic, and within the number of significant figures in our problem, even though I wrote that down as 1, let's pretend I wrote it down as 2, right? To two significant figures, we get the same answer, right? So why go through the work of the quadratic if we don't need to? And so when we have that situation, very small values of Ka that are at least 1,000 times smaller than the concentrations, right? So if your value of Ka is at least 1,000 times smaller than your concentration, you can get away with ignoring this small value of x when we add it or subtract it from something, and that makes our calculation easier because it will avoid using the quadratic. Okay, so let's consider this solution, right? So we've got 0.05 molar HC2H3O2, just to remind ourselves, right? That's acetic acid, right? One we should recognize the formula of. And it has a Ka of 1.8 times 10 to the minus 5. And so let's figure out the hydrogen ion concentration of that solution and the pH. Okay, so we write out our acid dissociation, right? Our acetic acid in aqueous solution is going to be in equilibrium with hydrogen ions and acetate ions, right? And if we look at our ice table, right, we have our initial concentration, which is 0.050 molar, none of that, none of that. that will change by x plus x plus x. When we reach equilibrium, we'll have 0.050 minus x, x, and x. Right? So if we plug all of those things into the Ka expression, right, you get that the Ka is equal to x, right, products over reactants, right, and all that is equal to 1.8 times 10 to the minus 5, right? And if you expand that out, you get a quadratic that's 0 is equal to x squared plus 1.8 times 10 to the minus 5x minus 9 times 10 to the minus 7. And if you solve that, you get x is equal to 9.397 times 10 to the minus 4. And that's equal to the concentration of hydrogen ions. Right? If you make the assumption, right, we can see here that, this is a small number. Maybe it's small enough that it won't make any difference here. So let's try that. Let's try ignoring that and work the problem that way. And so we end up then with 1.8 times 10 to the minus 5 equals x times x divided by 0.05. We get 9 times 10 to the minus 7 is equal to x squared. And when you do that, then you get 9.486 times 10 to the minus 4 is equal to x, which is equal to an estimate of the hydrogen ion concentration, right? And so we get, right, they're a little bit different, right? They're a little bit different. So, right, carrying on here, right, we've got this answer when we made the estimate ignoring x, and this answer without x, or when we used x and went the long way through the quadratic, right? Remember, I didn't write that all down. That's not really that much of a difference, right? If we take our exact answer, well, let's take our estimated answer, our 9.486 times 10 to the minus 4, right, minus a 9.37, or 397, let's fix that, 97 times 10 to the minus 4, right, and divide that by the exact answer, 9.397 times 10 to the minus 4, we get 9.471 times 10 to the minus 3, or less than a 1% error, right? In these kinds of problems, given that most of them are only being worked to two significant figures, a less than 1% error is acceptable. And so we would say, in this case, we could have saved time by doing the estimate instead of by going the long way through the quadratic. In general, the way you tell is this, right? You take the number, right, you were ignoring it against, right? You take your x that you found, in this case our 9.486 times 10 to the minus 4, and we divide that by the number that we were adding it to or subtracting it from. In this case, the 0.050, right? If we do that division, right, you end up with 1.9 times 10 to the minus 2, or 1.9%, right? If that number is less than 5%, then the estimate is acceptable. Okay? So in the long run, right, when we're working these weak acid, weak base problems, right, start off by looking at your value of your Ka and comparing it to your concentration, right? If your Ka is about 1,000 times smaller than your concentration or more, you should try the estimate first. Then at the end, check and see if the value that you got was less than 5% of what you ignored it against. And if it is, then your estimate is acceptable and you don't have to go through the quadratic form. And you can save yourself a lot of time over the course of doing a number of problems by avoiding doing the quadratic and making the estimate. All right, so let's consider this problem, right? We've got a 0.20 molar solution of HONH2, which is a compound called hydroxylamine, right? It's got that nitrogen in there, so we suspect it's going to act as a weak base. So we look up its Kb. Its Kb is 1.07 times 10 to the minus 8th. That's an 8, right? And so we write out our equilibrium, right? These nitrogen-containing bases, even though that has an OH on it, it's not going to release that. It's going to react with water. It's going to take a hydrogen ion from water, leaving a hydroxide ion, and we're going to get our hydroxyl ammonium ion as the other product. And so we can set up our ice table, right? Our initial concentration is 0.20. We don't care about water because it's a pure liquid, right? 0 hydroxide ion, 0 hydroxyl ammonium ion. Our change is going to be minus x plus x plus x. When we reach equilibrium, we're going to have 0.20 minus x. We're going to have x. We're going to have x there, right? But because our Kb is such a small number relative to our initial concentration, we're going to first, before we work way too hard, try to just ignore that number, okay? And we'll work the problem ignoring, subtracting that tiny number from that big number, right? And so when we work this out, right, if we put it into our Kb, we get 1.07 times 10 to the minus 8th, that's our Kb, is going to be equal to x times x divided by 0.20, right? And when we multiply through by the 0.20, we get 2.14 times 10 to the minus 9 is equal to x squared. If we take the square root of both sides, then we get 4.63 times 10 to the minus 5 is equal to x, right? That's great. This is where we have to remember, though, right? How did we define our x, right? Our x here at the end is our hydroxide ion concentration, not our hydrogen ion concentration, right? So that's the hydroxide ion concentration. If we want to know the hydrogen ion concentration of this solution, we need to use our expression, right? That our, right, Kw is equal to the concentration of hydrogen ions times the concentration of hydroxide ions, right? So we know that 1.0 times 10 to the minus 14 is going to be equal to the concentration of hydrogen ions times that 4.63 times 10 to the minus 5, right? So 1.0 times 10 to the minus 14 divided by 4.63 times 10 to the minus 5 is equal to our concentration of hydrogen ions, which is equal to 2.31, oh, I'm sorry, which is equal to 2.16 times 10 to the minus 10, right? And so our pH would be 9.67. Now, I jumped ahead, got all excited, right? Before we did all that, we should have looked at this number and this number, right? If you divide the 4.63 times 10 to the minus 5 by the 0.2, right, you get 2.31 times 10 to the minus 4, which is clearly less than 0.05, which would be 5%. So our estimate was good. We don't have to go back and do the quadratic, and so then we could come up and finish our problem. Okay? So that's the way you deal with problems involving small equilibrium constants. In our next one, we'll deal with small equilibrium constants where our products are not necessarily zero.